Hello, my name is Jude Socrates, and welcome to my video on Introduction to Proofs. If you're taking linear algebra, you probably have taken 2 semesters worth of calculus. And in those calculus classes, you probably saw a few proofs, but linear algebra is the first time, most likely, that you're expected to actually read, understand, and write your own proofs. So maybe you're feeling a little bit anxious, maybe a little bit excited. But in this video, we will walk you through the first homework problems that you will solve about proofs, and we'll give you some tips, some examples that will directly help you in solving those problems. Okay, so let's take a look at the first batch of theorems that you'll be asked to show. These are all from the main theorem of section 1.1, which talks about the properties of vector arithmetic. So, you're going to be asked to prove a closure property for addition and scalar multiplication, commutative property, the associative property, a distributive property, and so on. Now, in the text, there is an example which shows how to prove one of the properties. So, let's go to that example. All right, so here's that example. We are going to prove that for all vectors v from Rn, and for all scalars r and s, the quantity r plus s times the vector v is exactly the same as r times v plus s times v. So this looks almost exactly like the distributive property that we have for real numbers. And in fact, that is something that we are going to see in a few minutes. In fact, all of the properties that you're going to prove in section 1.1 are very much like the properties of real numbers that we see in basic algebra. So we are going to see later on that there are actually 11 important properties of real numbers that will help us to complete these proofs. Okay, so let's jump in. The key to solving this problem is to simply express the vector v in proper notation. So there we have it. V is written as bracket v1, v2 through vn, where of course each component v sub I is just a real number. So when we perform the scalar product r plus s times v, we will replace v with the vector v1, v2 through vn, and then we can perform the scalar multiplication. So in the first component, we see quantity r plus s times v1, in the second r plus s times v2, and so on. So based on the ordinary distributive property for real numbers, we can expand each of these products. So r plus s times v1 is just the same as r times v1 plus s times v1, and so on. So we repeat that process for every component. So now let's work on the right side of the equation. We want to compute r times v plus s times v. So again, we will replace v, and there are 2 of them, with the notation v1, v2 through vn. So now we perform the scalar multiplication. So r times v is rv1, rv2 through rvn, and s times v is sv1, sv2 through svn. Now, by the definition of vector addition, this sum is just rv1 plus sv1 in the first component, rv2 plus sv2 in the second component, and so on. And of course, what we see at the bottom is exactly the same vector expression that we got from the left-hand side. So this shows that the quantity r plus s times v is exactly the same as r times v plus s times v. So now let's look at the second group of theorems that you are going to do in your section 1.1 homework. So these are a little bit trickier because you're only allowed to use the 10 properties of vector arithmetic that are found in theorem 1.1.4. So you're going to be asked to show that the zero vector is unique, and the additive inverse of a vector is also unique. You will be asked to show the cancellation law for vector addition, and that the negative of a vector is just that vector times -1. What we're going to see today is something that will help you in the next 2 problems. and that would be the multiplicative property of the scalar 0, which is that for all vectors v, when you multiply v by 0, you will just get the 0 vector. That kind of makes sense, right? And similarly, if you take the 0 vector and you multiply it by any scalar, then you will again get the 0 vector. Okay? We will put those two properties together into what's called the zero factors theorem for vectors, which is for all scalars k and for all vectors v, the product k times v is the 0 vector if and only if either k equals 0 or v equals 0. So now we come to the field axioms for the set of real numbers. These are found on page 4 of the 4th edition. Here we will find 11 properties of real numbers, which we have seen since we started learning arithmetic and algebra. So what are these field axioms? The first two are called closure properties. So they say that for all real numbers x and y, x plus y is also a real number, and the product x times y is also a real number. The next two properties are the commutative properties. They say that for any two real numbers x and y, x plus y is the same as y plus x times y is also the same as y plus x. The next two are called the associative properties. Now we have three real numbers. For all real numbers x, y, and z, x plus the quantity y plus z is the same as the quantity x plus y plus z. And similarly, x times the quantity y times z is the same as the quantity x times y times z. Now we have the distributive property. For all real numbers again, x, y, and z, x times the quantity y plus z is the same as x times y plus x times v. In the next two properties, we have what are called identities. We know them as the numbers 0 and 1. There exists a number 0, so that for all real numbers x, x plus 0 is still x. And of course, 0 plus x is also x. And similarly, there exists a special number 1, and 1 is different from 0, so that for all real numbers x, x times 1 is the same as x, and 1 times x, of course, is the same as x. Our last two axioms are about inverses. We know them as negatives and also as reciprocals. Every real number has a negative x, so that if you add x to negative x, you will just get 0. The last axiom is a little bit different because it only applies to non-zero numbers. We know we can't divide by 0. So this axiom says, for all real numbers x which are not 0, there exists a reciprocal 1 over x, so that when you multiply x to 1 over x, you'll just get 1. So again, we have seen these properties since we started learning arithmetic. So for example, we have an application of the associative property. 3 plus the quantity 5 plus 2 is 3 plus 7, since we do 5 plus 2 first, and 3 plus 7 is 10. But if you add 3 and 5 first, you get 8, followed by the plus 2. Again, you get 10. So of course everybody knows that, and we don't even put parentheses anymore. We often just write 3 plus 5 plus 2, and we get 10. But the reason that we can do that is precisely because of the associative property. Here we also have an application of the distributive property. If you have 4 times the quantity 3 plus 2, you do the addition first, so that's 4 times 5, which is 20. But you can also think of it as 4 times 3 plus 4 times 2 by the distributive property. What do we get? 4 times 3 is 12, 4 times 2 is 8, and 12 plus 8 give you 20. So of course you get exactly the same thing. So those are the associative and the distributive properties. Now, there were a lot of words in the 11 axioms that we saw about the real numbers. So we can make them a little bit shorter using these abbreviated sentences. So we can say that for all real numbers x, y, and z, we have the closure properties, the commutative properties, the associative properties, the distributive property, there's only one of them, the additive identity, the multiplicative identity, additive inverses, and multiplicative inverses. So for example, when we apply the commutative property, if we can see that we're adding two numbers, we don't have to say the commutative property for addition says this. It should be pretty obvious. Okay, so now we come to our first major example. We will prove this theorem using only the 11 field axioms and a couple of other techniques and devices that we'll mention when we get there. So we are going to prove the multiplicative property of 0. It says, for all real numbers a, 0 times a has to be 0. And of course, a times 0 is also 0. And of course, you might say, well, everybody knows that. You take something, you multiply it by nothing, you get nothing. Well, that's the problem with mathematics. How are we supposed to know what we believe, what we can use, and whether or not our proof is right or wrong? So, in this example, we are only going to use the 11 axioms that we saw for real numbers. And notice, in those 11 axioms, none of them said anything about a times 0. It was only about 0 plus x being 0, and there is a negative x, so that x plus negative x will get you 0. There was nothing at all about 0 times x, right? So, let's start this proof, okay? We are given a real number a. We want to show that 0 times a equals 0, and of course, so is a times 0. Well, where do we start? By closure, we know that when we multiply two numbers, we again get the number, okay? So we can write that down. By closure, 0 times a has to be a real number. Okay? Now, we also want to show that a times 0 is also 0. But isn't that just the commutative property? By the commutative property, 0 times a is exactly the same as a times 0. Okay? So if we can show that 0 times a is already 0, then we don't have to show that a times 0 is also 0, because 0 times a and a times 0 are exactly the same. Now, we said earlier when we first read the problem, we said that the only thing we know about the number 0 is the additive identity property, which says that if you add 0 to any number, you get exactly the same number. So let's bring back that property. Let's paste it in. Here you go. There exists a real number 0, so that for all real numbers x, x plus 0 has to be x. Okay? So now, what are we going to do with this axiom? Well, what if we make this x also equal to 0? X could be any real number. So therefore, we can say, let's see what happens when x is 0. If we substitute x equals 0 into this axiom, we get 0 plus 0 equals x. Well, who is x? 0. So 0 plus 0 equals 0. And the third part, oh, we also get 0 plus 0. So it doesn't tell us anything new, but it does tell us, reassure us, that 0 plus 0 is equal to 0. And again, that's something we knew in the second grade, but that's because these are the properties of real numbers. Okay, so now we have something to work with. We want to show that 0 times a is 0. Okay, so this equation tells us that 0 plus 0 equals 0. What we're going to do next is called the substitution principle. If two quantities are exactly the same and you perform the same operation to both sides of the equation, then the new equation that you get should still be valid. So in this case, let's multiply both sides of the first equation by the number a. So let's multiply the equation, and that would be 0 plus 0 equals 0 by a. All right, and so we get 0 plus 0 times a equals 0 times a. This is good because now we can apply the distributive property on the left side to change 0 plus 0 times a into 0 times a plus 0 times a. By the distributive property, the left side becomes 0 times a plus 0 times a. So I can take this and I can copy this. Plus 0 times a equals another 0 times a. Okay, so let's think about that equation. It's all 0 times a. 0 times a plus 0 times a is still 0 times a. So that kind of sounds like an algebra equation, don't you think? I don't know what this is. Let's call it, I don't know, x. X plus x equals x. Solve for x. What is x supposed to be? Because what we're looking for is 0 times a, right? So 0 times a is here in 3 places, and we want to show it's 0. Now it's very tempting to simplify the left side to 2 times 0 times a, but I'm going to stop you. That's not the right way to go. So let's think about what I said. X plus x equals x. So instead of putting 2 times x, let's think about subtracting. What axiom allows us to subtract? Additive inverses. So let's write that down. By the axiom on additive inverses, 0 times a has an additive inverse. Okay, so let's write it as the negative of the quantity 0 times a. Okay, it looks a little awkward, but I want to put those parentheses down. So what we're going to do next is we're going to add this additive inverse to both sides of this equation. Now, when we do that, I am going to put parentheses around these two numbers. Now, why is that? Well, these two numbers are supposed to be added together first before we add this third number. Okay, so let me show you. Let's add this additive inverse to both sides of the previous equation. Okay, so we get negative 0 times a plus the quantity 0 times a plus 0 times a equals the negative of 0 times a plus 0 times a. So notice that there are 3 things that we are adding on the left side of the equation. What axiom contained 3 things? Well, there were several of them. But here, we have 2 additions. So why don't we use the associative property of addition? By the associative property of addition, the left side becomes, so we will add together negative 0 times a plus the first 0 times a. And then on the outside, we will add the second 0 times a. Let's just keep the right side the same for now. But, well, let's think about that right side. You have the negative of something added to the same thing. We said that that's 0. That's the axiom for additive inverses. But wait, it also appears over here now, because we're adding negative 0 times a to 0 plus a. So this also becomes 0. So by the axiom on additive inverses, both sides now become 0 plus 0 times a equals, on the right side, again 0. Now we're almost there. Check it out. I don't know what 0 times a is, but when we add it to 0, we get 0. Now, don't we have something that says if you add 0 to anything, you get that same thing? So here we have it. I don't know what 0 times a is, but if you add 0 to it, it's still 0 times a. By the additive identity axiom, the left side becomes, it's just 0 times a, and on the right side, we get 0. Ta-da! That's what we wanted to show, and so that is now the end of our proof. Well, at least for the first problem. Okay, I hope that you enjoyed that, but now we're not yet done. We are going to do one more proof, and we are going to kick it up a notch. We are going to prove the zero factors theorem. This tells us that for all real numbers a and b, the product a times b is 0 if and only if either a is 0 or b is 0. And again, you know this. If you multiply two numbers and you get 0, one of them had to be 0. It doesn't have to be that both of them are 0. You only want one of them to 0. Okay, so what's another way of thinking about it? If you have two numbers which are not 0, then the product that you get should not be 0. 3 times 5, neither of them is 0. You get 15, that's not 0 either. But of course, 3 times 0 will be 0. So, this problem is more complicated because of this phrase in the middle, if and only if. So, when we prove something which says if and only if, it means it's twice the work. There is a forward direction and there is a backwards direction. Okay, so let's do an outline. The forward direction says we are given a times b equals 0. We want to show that a equals 0 or b equals 0. That's the forward direction or the forward implication. There's a backward direction. So this time we are given that a equals 0 or b equals 0. We want to show that a times b equals 0. So anytime you see the phrase if and only if, unfortunately, it's twice as much work. Alright, well, let's look at the two things that we have to show. Is one of these already familiar to us? Let's look at the backwards direction. We already know that a is 0 or b is 0. Didn't we just see something like that? Right? We showed that if you take any number a and you multiply it by 0, you get 0. So if b is already 0, then we get a times 0, which is 0. Oh, that's great. If we knew that b equals 0, then what do we have? Well, we have a times b is now a times 0, and that will be 0 by our first example. Okay, that's great. Okay, but unfortunately, there's an or in the sentence. We don't know if it's A, which is 0, or if it's B, that's 0. But is the other possibility any harder? However, if A equals 0, what's going to happen? Then we get, what is A times B this time? A times B will be, it's A this time, which is 0, so 0 times B. Now wait a minute. Is that really something different? It still says 0 times a number. So it really doesn't matter, does it, whether we call that number A or B? What's in a name? It's still a number. So 0 times B, which is still 0. Because B is any real number. So it's really not that different. Whether it's A that's 0 or B that's 0, we still get A times B is going to be 0. So it's really the forward direction, which is something new now. What we are told is that the product of two numbers is 0. We don't know anything about those two numbers, except they're numbers. That's all that we know. They're numbers. Okay? So what are we going to do? What we will do is what's called a case-by-case analysis. We will break down our proof into two cases, two possibilities. So case 1, we will assume that A equals 0. And you might start to complain, now wait a minute, are we allowed to assume that the conclusion is true? No, of course not. That would not be logical. So how do we get away with it? Well, what we're saying is that there is at least one possibility. Maybe A is already 0. But of course, there is another possibility, right? So there is a second case. It is also possible that A is not 0. So those are our two possibilities for the number A. A could be 0, but the opposite of that is A is not 0. Okay, so what happens if A is already 0? Well, this says we want to show that A equals 0 or B equals 0. Well, if A is already 0, that conclusion is already true because we're only required to show that either A is 0 or B is 0. So I'm going to write this. In this case, the desired conclusion, which is, I'll put it in quotation marks, A equals 0 or B equals 0, there you go, is already true. All right, so we have shown what it is that we want to show. What about the other case? It is, of course, possible that A is not 0. How are we going to complete the proof? Well, if A is not 0, the only other possibility that has to happen is that B equals 0. So, to complete the proof, we must show that B equals 0. Okay, so how do we do that? Well, we are given that A times B is 0. So let's remind ourselves of that. Recall that we are given that A times B is 0. Okay, in case 2, we are now assuming that A is not 0. A is not 0. Now, I know that it was like 25 minutes ago or so, but when we saw the field axioms for the real numbers, wasn't there a special axiom that applies only if a number is not 0? Let's bring those axioms back. Aha, here they are again. And of course, it's the last axiom. For all real numbers x, where x is not 0, there exists a reciprocal 1 over x, so that when you multiply x by 1 over x, you will just get 1. So that is what we're going to use for our symbol a. In case 2, we know that a is not 0, so therefore it has a reciprocal. So now, let's use the reciprocal of a and multiply it to both sides of this equation. Since a is not 0, it has a reciprocal 1 over a, and we can multiply the reciprocal to both sides. So we get 1 over a times the quantity a times b equals 1 over a times 0. On the left side, we're multiplying 3 numbers. So again, we can think of the associative property. On the right side, 1 over a is again a real number. So we can apply our first example and get 1 over a times 0 is again just 0. By our last example, the right side is just 0. By the associative property, the left side is quantity 1 over a times a times b, and on the right side we have 0. And now we're almost finished. The left side has 1 over a times a, and we know from the last axiom that 1 over a times a is just 1. By the axiom on multiplicative inverses, the left side simplifies to, we just get 1 times b, and on the other side we get 0. But wait a minute, one of the axioms also says that 1 times b is just b. Which one was that? That's the axiom on the multiplicative identity. And the axiom on the multiplicative identity, the left side becomes just b equals 0. And there it is. To complete the proof, we said we had to show that b has to be 0. There it is. B must be 0. So there you go. I hope you liked those 2 examples. And I also wanted to remind you before we go that the last 3 problems from exercise number 7 are very much like the 2 theorems that we proved. So there is a multiplicative property for the scalar 0, which says that for all vectors v, 0 times v is the 0 vector. And we also have a similar property for the 0 vector, where this time, if you multiply the 0 vector by any scalar k, you again get the 0 vector. So there's a hint here and a hint here, and our second example on the zero factors theorem also generalizes to vectors. For all scalars k and for all vectors v, then k times v is the 0 vector if and only if either k is 0 or v is the 0 vector. Okay, so it's now up to you to do your homework. I hope that you learned enough from this video to finish your homework. But if you want to watch the video again, that's the great thing about having a video. Enjoy the rest of your day, and I will see you in our next video. Bye!